Uh, Let me start by reviewing sintering, because this is an area which I have through my years understood is very little really understood by most of the students. On the slide over here on the computer, I have shown 6 different shapes. All of them are sintered. This particular one on your left and the next one are highly porous. This one has got less porosity. The grain sizes are much smaller than you can see over here. The last one, this is also sintered. The grain sizes are fine. And so, sintered ceramics, in terms of, I am not talking of transparent ceramics, but sintered ceramics can have microstructure like any one of these depending on what is the end use. But before I take on sintering, let me bring up something which I had said in my earlier lecture as to how they are compacted. Here is a case where identical sized alumina fine powders were taken and they were compacted by 2 processes. One is the colloidal processing. The particles were taken in the colloid form and then allowed to settle down. And this one was slip casting, the way your bathroom fixtures are made. These were fired at 1200 degrees centigrade. Look at the difference in microstructure. The one on your right, the one which was slip cast, shows that sintering has not even started. Whereas the one on your left, which started off with identical powder sizes, we see large number of grains growing. If we take this to 1400 degrees centigrade, you will see that the one which was done by colloidal processing, where the packing was much more uniform, the microstructure is very dense. Whereas the one which was made by slip casting, the way your bathroom fixtures are made, there is a lot of porosity in it. All these dark spots are pores. So, grain growth has not occurred over here to the extent it has occurred in this one. So, even though we have started with the same identical powder, have merely shaped the green body through colloidal processing, which gives a better green body, green means unfired body, than the slip casting method, the microstructure shows a drastic change. This is at the heart of basic sintering. How are the particles packed? Now, based on my years of teaching, let me say differentiate various terms. Densification. Here are some idealized spherical granules of ceramics which have been pressed and heated. First of all, here what we see is the grains have grown. Yes, there is a reason to draw even these 4-sided structures, as will become apparent later. So, what has happened is you do not see any porosity along the grain boundaries. So, here densification has occurred, and on further heating, grains have grown very large. Now, this is what is required in sintering of ceramics, especially where we are talking of high strength, high performance ceramics. What we certainly do not want in industrial ceramic fabrication and processing is grain coarsening. These grains are there to start with. At the end of the sintering process, what has happened? Grains have merely grown larger. The porosity has remained and grain sizes have grown very large. This is what is definitely not required in ceramic processing. Why? Let us look at the reason. This is a plot of, in this axis, I have put in percentage of theoretical density. And in this axis, I have written what is the final grain size. If only coarsening happens, we will see a huge increase in grain size, as in this case, without any increase in density. This is not what ceramic processing wants. But yes, when we want highly porous ceramics, we do resort to this technique where I want highly porous materials. If, on the other hand, I have got good sintering, what we will see is this curve, densification plus grain growth. First, as the densification occurs, the density increases. And then, when grain growth takes over, the theoretical density has been reached and the grain size increases. This is what we ideally wish to achieve in ceramic processing. However, in most of the cases, we are hindered by the fact what we have is coarsening and densification. In most normal cases, we have grains getting coarsened and densified. I had showed you a graph earlier today where you had seen large size grains mixed with fine grains. That is due to this coarsening and densification. If I look at this right hand side of the graph, which is a summary, is this: if I am drawing the pores, this is the starting material. If I have got coarsening, what will I see? Pore size increase, the grain size will increase. But if I have got proper sintering, I will have the pore size decreasing and then the grain size increasing. So this particular graph corresponds to this particular graph over here. Now, this is an idealized version of what we wish to achieve, but this course will take you through the ways it can be done. Now, to define sintering, this graph, this plot tells you what sintering is. Here I have drawn 4 idealized spherical particles. During sintering, what happens? Mass transfer takes place. Sintering only happens if the distance between the two centers decrease, which has happened over here. There has been a shrinkage. Only this case do we call real sintering has happened. This, whether sintering has happened or not, can be determined by dilatometry. There are various versions of it. but let me draw one simple version. This is a furnace, a tubular one, which is heated resistively, or for very high temperature materials can be heated inductively. This is a platen which is fixed. The ceramic whose sintering is to be studied is mounted inside the furnace in an uniform temperature zone, and then it can be its length, this length is monitored by any of the means. It can be a very sophisticated means where you use optical techniques, or it can be a very fine spring loaded meter which measures the length. So, as you heat it, you keep on measuring if there is any change in length. So, at the end of the day, at the end of the temperature, if the final length is somewhere over here, that is, a shrinkage has occurred to the extent of del L, only in that case you have sintering. If this had not occurred, if the shape, if the length had remained unchanged, it would have meant merely grain growth, coarsening, etc., where no dimensional change has occurred. While sintering can be followed very easily by dialitometry, that is measuring the length, grain growth or coarsening can be followed only by looking at it through scanning electron microscopy, optical microscopy, since the external size has not changed. Now, sintering and ceramics, how does it happen? Sintering is not new to ceramics area, metals are also sintered. But to remember one thing, that what constitutes sintering, I had stated over here that the distance between the centers has to decrease, so that there is an overall decrease in the dimension. Now, let us take three mechanisms which do not lead to sintering. These are two particles in contact. There is a neck area where they have joined. The driving force is here to reduce the area of the neck so that the free energy decreases. One of the ways that happens is evaporation condensation over here, surface diffusion and lattice diffusion from surface. None of these mechanisms lead to sintering, because at the end of the day what we will land up with is the two grains, maybe the neck area would have flattened out more, but the distance between the centers would not have changed. The only mass transport phenomena which leads to sintering, that is, two grains are in contact and which diffusion process will allow it. One is the grain boundary diffusion, which is a diffusion over here, or this particular diffusion, both of which occur through the area which is in contact. And over here, when this mass transfer takes place, shrinkage will occur. It is only through these two sintering processes, that is diffusion from the grain boundary region or region between the powder particles, can sintering ever take place. Now, what are the things that happen during sintering? To my left is a diagram of three particles in contact. You can assume three tennis balls, three table tennis balls, which are placed like this, and they are being heated. First of all, through these mechanisms, there is diffusion from the grain boundary or the region between the powder particles. What happens is neck growth starts happening over here. That is, I have shown you this is a neck which has formed. So basically a neck forms over here. This neck forms over here. You can imagine a ball with a flattened surface. So here what happens is this sort of a neck starts growing. As more and more diffusion occurs, what happens is these surfaces tend to flatten out. They tend to flatten out in this fashion. This can be ideally described how it happens is by taking this diagram of the tetrachi dodecahedron. It is a 14-sided polyhedron with 6 squares and 8 hexagonal sides. These are the square sides and these are the hexagonal sides. Now all of these diagrams are from open source Wikipedia, and so the same license condition applies. Now how do I make a tetrachi dodecahedron? The starting ground is this octahedron. If we cut these parts of the octahedra, what will happen is we will generate this surface. If we cut these parts of the octahedra, I will generate this one. So basically what tetrachi dodecahedron is basically a section part of an octahedra. Now whenever, the reason why I bring in is this is during sintering, these tetrachi dodecahedron like faces are generated. These tetrachi dodecahedron like faces are generated, and the ceramic particles are packed during sintering accordingly. I will come back to this diagram a bit later. During this stage of sintering, this part to this part, when neck growth is occurring, and even before the neck growth has occurred, we have got 3 stages of sintering. One is from here to the here, there is the initial stage when particle rearrangement can take place. This is called the second stage of sintering, because here the centers are coming together closer, leading to this particular stage of sintering, and then the final stage. Let us go over each of the stages one by one. The initial stage of sintering, as I said, occurs somewhere over here. Here what we have is rearrangement and starting of the neck formation. Now this can be shown from this diagram. That is, the rearrangement is starting to take place, neck formation has started occurring, and this is the initial stage of sintering. At the second stage, which is the intermediate stage, this particular stage and here, what we have is neck growth and volume shrinkage. Because if these necks grow larger and larger, it means the packing is increasing, which you can see over here. Lengthening of grain boundaries. Let me say what it means. If this was a diagram during intermediate stage of sintering, in the initial stage of sintering, in the intermediate stage of sintering, what we are seeing is the necks have grown larger, grain boundaries have got lengthened, these grain boundaries have got lengthened, and both the grain boundary lengthening and with a concomitant increase in grain boundary neck growth, this is what happens. A very large amount of neck growth with grain boundary lengthening has occurred over here as compared to over here. This is what happens at the second stage of sintering. At this stage, we have very high shrinkage, with very high shrinkage with continuous pore phase. As you can see, these pore phases are now continuous, as opposed to the discontinuity they had earlier. Here the pore phase was discontinuous much more. Over here at the intermediate stage of sintering, at the near the end of intermediate stage of sintering, the grain boundaries have lengthened, the pore phases have become continuous. In the final phase of sintering, what do we expect? In the final phase of sintering, what we expect is the grains to grow much more larger. And because the grains are growing larger, in this diagram, as the grains will grow much larger, the pore phases will again become discontinuous. This is what you see over here. The grains have grown significantly larger and the pore phases, they have become discontinuous. And hence, what we have in the end stage is more of porosity reduction and finally grain growth with porosity elimination. Here you do not see much of a porosity at all. These are large uniform grains. How does it happen? Let me go back to the diagram from where I started. This particular diagram. I had shown that here neck growth is happening. From there, what we are getting is these flat surfaces are opening up to form this. Essentially, what we have over here are over here are these are the cylindrical pores that I have drawn over here, and I have got the grain surface over here. This is the grain surface over here. Similarly, there will be other grain surface over here. Now what happens is, this is a cylindrical pore, the vacancy concentration will decrease. So mass diffusion will occur, and as more and more sintering occurs, the size of this cylindrical pore decreases till finally they become so thin that the pores are isolated at these ends, leaving a simple grain boundary. Leaving a simple grain boundary. That is, these plates which represent the grains will be over here, the pores will be isolated over here, and finally this will lead to formation of a ceramic sintered body, which in an idealized fashion is pore free. Now this is, I admit, very, very idealized in shape. In reality, we do not expect anything more than this. In reality. Again, to review the sintering process, what I would say is, in the initial, this is the initial stage of sintering. In the initial stage end, mass transfer along grain boundaries has occurred, leading to development of the necks. As the sintering has proceeded, the grains have flattened out. The grain boundaries have increased. The pores have started concentrating at the grain boundaries. And at the final stage, they are only at the corners, leaving the grains with very few sizes. If I look at this over here in this particular diagram, these are sort of grain boundaries we expect. These are sort of grain boundaries we expect over here. If we can achieve this, we have achieved a lot. But in most cases, what happens is, due to the grain boundaries moving very fast, pores tend to get included within the grains, as it has happened over here. In this particular microstructure, the pore is within the grain because the grain boundary has moved very fast. The pore did not have the time to be removed, and as a result, all these closed pores are within the grains. This is a necessary hazard of sintering. Now, this is solid state sintering. I have not yet talked of liquid state sintering, which I shall take up in the next class. In the solid state sintering, what I have is I'll require this sort of a microstructure, this particular type of microstructure. And while I shall always try to avoid the ones with porosity. To have a good control over sintering, what we require is, hence, basically, to go back to my original graph, densification followed by grain growth. Now, one of the best books to look up, though I have not listed among books, I have said, is the one by Barsoom. This book by Barsoom deals with all the equations that you may need to know for understanding sintering kinetics. In solid state sintering, normally in a real life case, we have powders of different shapes and sizes. In most of the cases, we do not have spherical powders. We have jagged end powders. And one must appreciate the fact that at these sharp ends, sintering will occur much more faster than over here. So, if I have to get a very uniform microstructure of ceramics, I have to find ways to generate powders with spherical shape and size. During sintering, one of the things that we use are materials like, say, sintering aids. These are the materials which help in sintering, because sintering is nothing but a diffusion process, and we have to find ways to enhance the diffusion rate. These materials enhance sintering. One of the for example, the sodium vapor lamp, which uses alumina, uses TiO2, titanium dioxide, as a sintering aid, because otherwise much more higher temperatures would be needed to densify the alumina. You know, this particular alumina structure, let me look at the slide again. This particular structure, very easy to say, hey, the grain sizes are uniform, leading to a transparent ceramic. You know, here they have used titanium dioxide as a sintering aid, true. But they have also used another material which is grain growth inhibitor. So that none of these grains could grow. And because that matrix from which the sodium vapor lamps are made are based on alumina, the grain growth inhibitor used is MgO. As alumina reacts with MgO to give you MgAl2O4. What happens is, just using hexagons just to make sure I've got a reasonably uniform microstructure, though that is not always true. What happens is, these grain growth inhibitors, they grow on the surfaces, and as a result they prevent the grain boundary to move either way, thus retaining the fineness of the microstructure which you see in this particular slide to your right. This grain growth inhibitor has made this transparent alumina possible. These sodium vapor lamps are made by taking alumina as matrix plus 1% titanium dioxide, which is the sintering aid, plus 0.5% to 2% depending, magnesium oxide, and firing it at under hydrogen gas at anywhere 1750 degrees centigrade or higher. What the titanium dioxide does as a sintering aid is to abstract oxygen from the alumina matrix, create defects so that diffusion does occur. Otherwise, it would have required at least 200 degrees centigrade temperature more to generate to sinter the alumina, in which case even the presence of grain growth inhibitor would not have been sufficient to stop the grain growth of these in this particular microstructure. So we required a balance of low temperature, sufficient sintering aid which would abstract the oxygen, and a grain growth inhibitor. During sintering, I have already said, sintering can be followed by dilatometry. That is, you measure the length of the sample as you heat it. But what happens if during sintering a liquid phase is formed, which can happen if, let us say, we take alumina, silica, and add to it a small amount of sodium oxide. I referred to this much more earlier in the very first lecture. There is a sodium oxide. I have taken Al2O3 plus SiO2. Let me presume in the ratio of 70 mole percent, 30 mole percent, or 20 mole percent plus Na2O at the rate of 10 mole percent sodium oxide. This sodium oxide would melt at a very low temperature, react with the silica at 1000 degree. What would happen is, if this was a silica grain, the original silica grain, and the sodium oxide, molten sodium oxide on the surface of this grain, it would react with the silica, leading to formation of a liquid. The more the reaction of the sodium oxide happens with the silica, the more would be the amount of liquid increasing with a concomitant decrease in the size of the silica grain. So what we will end up is, this is a silica rich liquid. Now we have Al2O3 also. The silica rich liquid, as a very simple case, I am still keeping things very simple, would react with alumina. Now a new product would be generated, which is mullite, which is a mixture of alumina and silica. It is a compound, specific compound with a specific melting point. I am not taking up the composition because I shall do it when I discuss two-phase diagrams. So with time, what happens is, this silica rich liquid now starts getting in alumina also. All of this will be Al2O3 dissolving in this liquid. What would be expected? So this is the resultant silica grains, which were really honestly much more larger to start with, but now they are surrounded by a sea of highly siliceous silica rich liquid, which also has alumina also. Now as more and more alumina dissolves, what would happen? The liquid would get supersaturated with mullite. This mullite would precipitate. Most of these growths are dendritic. As a result, lot of entangling happens, and here the structure will have, the liquid will have a lot of mullitic grains out here. So when this is cooled to room temperature, what you will see is silica grains with mullitic needles intertwined here and there, plus a glassy phase. So here I have SiO2 grains interlocked with dendritic mullite needles in a glassy matrix. This is the microstructure. If you have a porcelain cup from which you drink your coffee, tea or whatever, this is what porcelain is. It is basically a ceramic body which is held together by the presence of glassy phase in the grain boundaries. So essentially, we may not really expect a decrease in dimension. There can be a decrease. It depends entirely on the volume expansion coefficient of the glassy phase over here. But the very presence of glassy phase in industrial applications can cause a problem. Is even though the silica will not melt below 1700, the mullite will also not melt below 1540, yet the material will soften at much lower temperatures due to the presence of glassy phase, which will soften at much lower temperatures. The other thing is the presence of this glassy phase is one of the things that we need to avoid in high strength ceramics. because this glassy phase will be the one that will be liable to fracture. Just like your ordinary drinking glass, it falls down and fractures. This glassy phase will also fracture very well. The ordinary teacup which you buy for say 4 rupees or 5 rupees as opposed to a Hitkari cup, where is the fundamental difference? Barring everything, the amount of glassy phase in the Hitkari cup is much lesser than in the 5 rupee cup. As a result, the Hitkari cup does not break that easily, whereas the common 5 rupee cup, porcelain cup that you buy, or the 10 rupee one, they break very easily. This is called liquid phase sintering. While I did say that liquid phase sintering has got its own drawback, that is, it gives us a glassy phase at the grain boundary, which will lead to mechanical failure or low temperature stability, that is, may soften at lower temperature. Yet liquid phase sintering at times is our mainstay of sintering. There are systems which cannot be sintered other than in the liquid phase, other than without generating a liquid phase. The silicon nitride bearings, balls that you saw earlier in today's lecture, they were made by reactive liquid phase sintering. The only trick that was added was that the glassy phase over in silicon nitride, they were converted to a crystalline ceramic. So here also additives can be used which can strengthen the glassy phase so that the properties of the liquid phase sintered body can be significantly increased. Silicon carbide is one such material. As you know, silicon carbide has got the same structure as diamond. It is virtually defectless. So how do we sinter silicon carbide? One of the methods that we do is we take silicon powder, add to it carbon powder, make it into a compact. Let us assume it's a rod which has got silicon plus carbon, and the whole thing is immersed in molten silicon bath. All of this, of course, under oxygen free conditions. The molten silicon migrates. This here silicon reacts with the carbon, generating ultrafine silicon carbide, which assists in the final sintering. One of the biggest problems here that we find in this sort of sintering is that we are frequently left with unreacted carbon. There is a center part, the carbon remains unreacted. Now, this also can be avoided if we take proper precaution. So, to sum it up today, I covered what is really sintering, and that it involves there has to be a shrinkage. If there is no shrinkage, does not matter what happens, it can be grain growth, coarsening. So, I try to emphasize with sintering there has to be a shrinkage. And then I talked briefly as to what the three different stages of sintering are: the initial stage, the neck formation, the intermediate stage, and the final stage where pores are eliminated. And I also talked of today what is liquid phase sintering. I shall take both of these forward in the next class before I wrap up sintering. Thank you.